So here today we'll see the variation of mass with the motion of the observer. That is, we are going to derive an expression for the relativistic mass. So for that, consider the diagram where two masses m1 and m2 are colliding with each other. This is m1 and this is m2. The m1 is having velocity u dash and m2 is having velocity minus u dash. Both these balls are, these velocities are measured with respect to the observer o dash. Now here the frame S is stationary frame and this frame S dash is moving frame, moving with uniform speed, say v. Now these masses m1 and m2, which are moving with velocity u dash and minus u dash, as it is moving in opposite direction, its velocity is taken as minus u dash. So these velocities are with reference to this moving frame S dash. Okay. Now, as I said, m1, m2 be the masses of the particles to be collided, u dash and minus u dash be the velocities of the particles m1 and m2 respectively in the frame S dash. Now let us find the velocities with reference to frame S, which is stationary frame. So we use the relativistic formula for velocity as we have derived in the last lecture. So u1 will be equal to, u1 is the velocity of this particle with respect to this frame, stationary frame, is equal to u dash plus v upon 1 plus v upon c square u dash. Similarly, the velocity of mass m2 with reference to this stationary frame is u2 is equal to minus u dash plus v upon 1 minus v upon c square into u dash. Now by applying the law of conservation of momentum, we say m1 u1 is equal to m2 u2 is equal to m1 plus m2 into v. After collision and before collision the momentum will be m1 u1 and m2 u2, and after collision it will be m1 plus m2 into v, because this frame is moving with velocity v. Okay. Now with in the frame S dash, after collision, this combined mass will move, or say will be stationary at the time of collision. This will be stationary, but with respect to this frame, this mass, both masses are moving with velocity v. So therefore this is the momentum before collision and this is the momentum after collision. Now, so if you put the values of u1 and u2 from the above equation, you will get the expression like this. Okay. Now if you just transfer the uh, m1 term here to the left hand side and you transfer this m2 term on right hand side, you will get this expression. Okay. So we have uh, taken m1 components, m1 terms on left hand side and the terms containing m2 on the right hand side. So if you solve this, so you will get the expression like this. Okay, by taking m1 common on left hand side and by taking m2 on the right hand side. Okay, we'll continue with this expression. So here, yes, so we have m1 and m2 common, and if you solve the bracket you will get the expression like this. Okay, so on the denominator 1 plus v upon c square into u dash, here also On right hand side, the denominator will be 1 minus v upon c square into u dash. Now, so if you again solve this, you will get m1 into u dash minus v square upon c square u dash upon this. Okay, the same expression we have. Now, here what is happening is we have taken this u dash on the left hand side, and the term containing minus sign is taken later. Okay, now this expression, now here we have m1 upon this, so m1 upon 1 plus v upon c square u dash. So this is taken together. Okay, because the numerator is same here, numerator is same here, therefore it can be cancelled. So the expression becomes m1 upon 1 plus v upon c square into u dash as written here, and m2 upon 1 minus v upon c square into u dash. Okay, now, these rigorous calculations can be simplified by replacing this term by x. Say v upon c square into u dash can be taken as a x, so that will be simplified. But even though we have taken as it is, okay. Now, m1 upon m2 can be written as 1 plus v upon c square u dash 1 minus v upon c square into u dash. So this can be taken as a x, this can be taken as x, and the things may be simplified. So even though you just remember, latter part we will replace this term by x. Okay, so that can be that looks simpler. So here, so this is the expression to be remembered. So we have now m1 upon m2 is equal to 1 plus v upon c square u dash upon 1 minus v upon c square u dash. You just remember that. So we have taken, this is the expression we have found after applying the law of conservation of momentum. Okay, that means momentum before collision is equal to momentum after collision. Now, we have now these relativistic relations, relativistic velocity. Un is equal to u dash plus v upon 1 plus v upon c square u dash, and we have u2 is equal to minus u dash plus v upon 1 minus v upon c square into u dash. Okay, now say again, I said we replace v upon c square u dash. These terms are repeating, therefore we replace this by x. Now the things become simpler like this. So now u1 is equal to u dash plus v upon 1 plus x, and u2 is equal to minus u dash plus v upon 1 minus x. Okay, so this replacement can be done here also. Okay, that may be simpler. Now let us see what happens. So if you take the value 1 minus u1 square upon c square, you have to remember this. So 1 minus u1 square upon c square is equal to 1 minus 1 upon c square is, and this is the value of u1 square. Okay. Now if you solve this again, you will get 1 minus 1 upon c square is there. If you solve the bracket, you will get u dash square plus v square plus 2 u dash v upon 1 plus x square. Again you multiply 1 by square, you take this 1 by square inside, you will get the expression like this. Okay, and again if you solve this, you will get, if you solve this by using by the cross multiplication, you will get 1 plus x square minus u dash square upon c square minus v square upon c square minus 2 u dash v upon c square. Okay, upon 1 plus x square. So our next step is, so here 1 plus x square can be written as 1 plus 2x plus x square minus u dash square upon c square minus v square upon c square minus 2x. Okay, so because this u dash v upon c square is here, and that can be replaced by say x. Now is equal to, yes, so 1 minus u1 square upon c square is equal to 1 plus x square. Okay, so this 2x may be cancelled. 1 plus x square minus u dash square upon c square minus v square by c square. Okay, now similarly, one can take the value of 1 minus u2 square by c square. So if you solve this in a similar lines, again with the same replacement of x, so you will get the expression like this: 1 minus u2 square upon c square is equal to 1 minus 1 upon c square into minus u dash plus v upon 1 minus x whole square. So if you just solve this again, as we have solved for the value of 1 minus u1 square upon c square, so you will get the expression like this. Okay, so again there is a cancellation of 2x on the numerator side, and you will get 1 minus u2 square upon c square is equal to 1 plus x square minus u dash square upon c square minus v square upon c square upon 1 minus x square. Yes, so you might have remembered we have 1 minus u1 square upon c square was 1 plus x square minus u dash square upon c square minus v square by c square. So here, so if you compare these equations, both equations, the numerator is same. The numerator value is same. Okay. So we can write, yes, 1 upon, sorry, 1 minus u1 square upon c square upon 1 minus u2 square upon c square is equal to 1 minus x whole square upon 1 plus x whole square. So here, so we have now the same expression we have now repeated. And what was x? Okay, before that, yes, we rearrange the equation like this: 1 plus x upon 1 minus x is equal to under root of 1 minus u2 square by c square upon under root of 1 minus u1 square upon c square. So as I said initially, we have derived the expression uh, like this: m1 upon m2 is equal to 1 plus v upon c square u dash upon 1 minus v upon c square into u dash. Okay, so this we have derived by applying the law of conservation of momentum initially. Now we know that this v upon c square u dash is nothing but x. So m1 upon m2 is equal to 1 plus x, and this will be 1 minus x, and the value is under root of, from this expression, under root of 1 minus u2 square by c square upon under root of 1 minus u1 square upon c square. That means what? That means, yes, we can write like this: cross multiplication, after cross multiplication of this, m1 into this term and m2 into this term. So that must be constant, because m1 is the particle, mass of the particle, and u1 is the speed, m2 is the mass of second particle, u2 is its speed, relativistic speed we can say. Okay, now here this multiplication is constant, that means this whole term must be a constant. So in general, so this is the general expression. We can replace this m by any m into under root of 1 minus u square by c square must be a constant like this. Now for the simplicity, or say for the approximation, we can say if m2 is equal to say m0, which is rest. So out of two particles, M2 is at rest. That means its mass is say M0. Yes. And as it is at rest, U2 must be equal to 0. Okay. So U2 is the speed of particle M2. So we have taken that this is M0 and this U2 is taken as 0. Okay. Then what will happen? And take M1 as M and U1 as V. What will happen? So that will be equal to m into 1 minus V square by C square, yes, is equal to M0. Because when you put this 0 here, under root of 1 minus 0 by C square becomes 1 only. So the expression become like this. And therefore, we can write like this, that is M is equal to, M is the relativistic mass. Okay. And this is the rest mass. So this is the relation between rest mass and the relativistic mass. As you observe, M is always greater than M0 as far as V is concerned. If V is larger, M is larger than M0. So mass increases. Mass increases. So relativistic mass is larger than the rest mass. So this is the important equation. Now then we'll see the mass energy equivalence. Okay. So we know that the force is the rate of change of momentum. Know that force is nothing but the rate of change of momentum, that is F is equal to d of dt of mv. So here d of dt of mv can be written as m into dv by dt plus v into dm by dt, because the mass is also changing with time, because mass is relative. Mass may change with time and velocity. Okay. So therefore its derivative contains, or say the derivative of mass into velocity is equal to mass into dv by dt plus velocity into dm by dt. So d is equal to f into dx. We know that work done is equal to force into displacement, and that work done is stored as a energy. So there is a change in energy. The change in energy is equal to force into displacement. So d is equal to m into dv by dt plus v into dm by dt into dx. So d is equal to mv dv. Okay. Because dx by dt, if you multiply this dx inside, okay, if you take this dx inside, so dx by dt becomes v. So m into v into dv by sorry m into dx by dt, that is equal to v, and this dv will be here. Here also v into dx by dt, that is equal to v square and into dm. So remember this equation as a equal to 1. Now let us start with the expression for the relativistic mass. So m is equal to m0 upon under root 1 minus v square by c square. That implies m square is equal to m0 square upon 1 minus v square by c square. If you just solve this, you will get m square is equal to, you multiply with the c square. Okay, on right hand side you multiply by c square on the numerator and denominator. You will get m0 square upon m0 square c square upon c square minus v square. So yes, again you take this c square minus v square term to the left hand side. That will be like this. And finally, m square c square minus m square v square is equal to m0 square into c square. So if you take the differential now, what happens? 2m dm into c square, because c square is constant, minus yes, 2m dm into v square minus 2v dv into m square, because here m and v both are variables, so therefore there are two terms. Okay, my is equal to this entire term is constant, therefore it is 0. Okay, so 2m dm into c square minus 2m dm v square minus 2v dv m square is equal to 0. Now this 2m 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 can be taken common. Okay, and it can also be cancelled. So what remains? Yes, yes, dm into c square. Okay, so let us see, dm into v square minus v square m, sorry, v into m into dv, like this. So dm c square minus dm into v square minus v into dm into, sorry, v into dv into m. Okay, dv will be here. Okay, so 1m will be cancelled, 2m will be cancelled from every term. So yes, if you rearrange this, you will get c square minus v square into dm. So we have taken this dm common, c square minus v square into dm minus mv dv is equal to 0. Then finally c square dm is equal to v square dm. Okay, c square dm is equal to v square dm plus mv dv. This is say equation number 2. Now if you observe this equation number 2 and equation number 1, the right hand side of both the equations, v square dm plus mv dv, here also v square dm plus mv dv, right hand side of equation number 1 and 2 is same, so therefore left hand side must be equal, so d must be equal to c square dm. Okay, so here c square dm must be equal to d. Now if you integrate, so what is the change in energy? Okay, and that change is occurring due to change in mass. And how the mass is changing? Mass, initial mass, or say rest mass, is m0, and its mass is increasing to m because of the velocity. So that change in energy can be calculated or say estimated by using the integration. Integration limits are from m0 to m. So e0 is equal to integration from m0 to m c square dm. So if you just solve the integration, you will get the value as e0 is equal to mc square minus m0 c square. Putting the limits of integration, you will get the expression. Now what is m0 c square? Is the rest mass. Okay, so here, so mc square is the, what is m? M is the relativistic mass, final mass. So mc square is the total mass is equal to E0 plus M0 C square, which is nothing but the, this is equal to energy E. Okay. Now this energy was the, this energy is nothing but the total energy. Change in energy because of the change in mass. Okay. Plus initial energy. Energy which was energy possessed by the particle having rest mass m0. Okay, so this was the initial energy, and this is the increase in energy. Okay, and this will be the total energy. So the total energy will be equal to mc square. Okay, and this mass is called the rest mass of the particle. If the particle is not moving, then its mass will be m0 into c square. So E is equal to mc square is the expression for the total energy of the particle. Okay, in the next lecture we'll see the uh, expression for the what is the effect of momentum due to the velocity. Okay, or say we'll derive an expression for the relativistic momentum.